let me recapitulate just a little bit from yesterday before I move on to explain what I'm going to do next. So essentially, what I wanted to explain yesterday, I mean, where we spent a lot of time trying to understand this diagram, is that the more fundamental aspects of the ADS-CFT correspondence. And okay, so let me backtrack from the very beginning to just put it into context again and tell you. So maybe now the general things I said at the beginning, they become clearer. So I started with this outline saying that on one hand side, I'm going to describe the foundations of ADS-CFT, and that's essentially what I did yesterday. And so I explained in great detail the ADS-CFT correspondence, which is our best understood example of gauge gravity duality. So, as I mentioned, I mean, this is a mathematical or example where there's a lot of symmetry. And so this means that mathematically and theoretically, it's very well understood, although there are not really concrete applications to the real world. And so one thing, my general message that I wanted to make at the beginning, so where was it? Right, first I had this very general definition of the word of duality. So this is a picture which you should remember from my lectures. So we have this very, very general example. And the special case here is that in gauge gravity duality, one of these two theories is a quantum field theory, a gauge theory, and the other one is a gravity theory. And I explained some features of this. And so what the point I really want to make, and from a general point of view, okay, starting with this very general sentence that physics is the science of matter and its interactions. So I introduced these two approaches, the one which I called fundamental approach, okay, by which I denote this idea of finding a unified theory of all known interactions. And as you probably know, there are actually four known interactions: electromagnetism and the weak and strong nuclear forces. And then, of course, there's gravity. And so these three here, they can easily be formulated as a quantum theory using perturbation theory. And so they are unified in the standard model of elementary particles. But then the question remains, how about gravity? And so there's a big challenge in this context. String theory was developed of finding a quantized theory of gravity, such that it then becomes possible to write a so-called theory of everything, where all of these four forces can be formulated in one theory. Okay, and there has been a lot of progress, especially also based on string theory or also other approaches. But okay, so I mean, there's not yet a universally established theory of quantum gravity, certainly not. So although there's a lot of progress, I mean, this is still a challenge. And so this is what many people work on, in particular also in the context of string theory. Okay, so this is what I call the fundamental approach. And okay, so this is more a theoretical issue. I mean, it's not so much that we want to be more able to describe some physical processes in some lab. It's just a theoretical concept that it would be nice to have one theory that fits all of the interactions. Okay, so it's a more kind of aesthetical, fundamental goal, if you want. But then I also introduced the so-called applied approach. Okay, so that's really the goal that normally people have in mind when they talk about physics, which is to describe observables and processes in systems with a given interaction. So here I have an example of a collision in a heavy ion collider, the RIG accelerator, and the superconductor. Okay, so there are some physical processes happening there, and in principle, you know which interaction. So here, this is electromagnetic interaction and spontaneous symmetry breaking, and here we have the strong force of the standard model, and QCD describes it, and so on. So that's in principle known. But there's also a challenge here, because in many of these cases, like for the high TC superconductors and also the heavy ion colliders, we are in a regime where there are so-called strongly coupled interactions. So don't confuse the strongly coupled interactions with the strong interactions. Okay, so the strong interaction is the force in the standard model that is described by quantum chromodynamics, QCD. But any interaction can be either weakly or strongly coupled. Okay, and and then I had this this diagram here. Okay, so that if a theory is weakly interacting, then you can actually, if you want to study the interactions of this particle, look individually at each interaction with each of these other particles, and this leads to this perturbative expansion. But if the coupling is very strong, then all the particles are very tightly connected, and you can just imagine they have these kind of springs between them. So if you want to describe the physics of this particle, then you have to, you cannot separately study the interactions with the other particles, because if you wiggle this particle, then the entire system is going to wiggle, okay? And that makes life very complicated, so this is a kind of challenge. I mean, it's also a challenge in theoretical physics to describe these strongly interacting systems. Okay, and this can arise in particle physics, in nuclear physics, in condensed matter physics. And sorry, so here I showed some examples where this can play a role. I mean, first of all, in QCD at low energies, so in the region where you, instead of having quarks and gluons, you have mesons and baryons. These are strongly coupled, and there's still lots of mysteries. So yesterday, somebody mentioned this Clay Millennium problem of finding the gap in this Young-Mills theory, and so this is an unsolved problem of physics. But also in high TC superconductors, the interactions are actually strong. And then generally in condensed matter physics, there are these strongly correlated electron systems, and so like high TC superconductors or heavy fermions, and more recently there's also something called the Weyl semimetals. Okay, so now here then the idea will be that now let's go again to this. Yesterday I explained in quite some detail this limit. Okay. So I explained this limit, and or in this diagram, which is here. So this is the same diagram, really. I explained this limit, and I said it was a two-step limit. Okay, one step was to send this n to infinity, but actually there's a second limit, and the second limit is to make this coupling very strong. Okay. So, but if we make this coupling very strong, we are in particular in just this regime that I just mentioned for this applied approach, okay? Because this means we cannot use perturbation theory. And this means it's very hard to calculate anything in this theory in this particular regime. But now we can then have the idea that we can use the duality. We can just take the duality for granted and say, okay, if we have this duality, the strongly coupled systems where we don't know how to calculate anything, we can, using the duality, replace by this supergravity on this particular theory and background. And so this theory is classical and it's weakly coupled. Okay, so this is also, so ADS-CFT is also a strong weak coupling duality. So here we have a weak coupling and it's classical. So this means this theory is extremely well solvable. I mean, there's all these very standard methods that you normally learn in your course on analytical mechanics in the third term or so of your studies. I mean, here in Würzburg, people learn this in their third term of undergraduate physics. Maybe in other parts of the world, this is even taught already in the first year at university. Okay, so what is the standard way of writing a physical theory? You write a Lagrangian, And from the Lagrangian, using the Hamilton principle, you get the equations of motion. And then, you get the equations of motion and you solve them. Okay, so this might be challenging because these equations might be nonlinear and so on, but there's no conceptual problem. Okay, it's a straightforward task to solve these equations of motion, and it's always possible, even if sometimes you have to resort to numerics or so. Okay, so then I can now say, I have this theory here, which is strongly coupled because I took this limit where I sent this 't Hooft coupling, which I mentioned yesterday, to infinity. But I can take this as a prototype theory at strong coupling. Okay, so this is something which I cannot solve using perturbation theory, as I explained in this diagram with these blue dots that are joined with these springs. But now here I have a theory that is very easily solvable. Okay, so the idea is, let's solve this theory and use this to make predictions for that theory. Okay, so this means, although ADS-CFT is really designed in the context of this fundamental approach, of finding a theory of quantum gravity, it may now also be used in this applied approach as a tool to look at processes in these theories that I can't calculate by any other established method. Okay, and so this is this applied side of holography or gauge gravity duality, and then the question is really quite different from finding a quantum gravity theory. But okay, so now I think the very main message I have, so this is, I hope, something philosophers would be interested to think about. Okay, so I defined this fundamental and the applied approach. I hope it's very clear what I mean by this. I just mentioned it right now again. So, so gauge gravity duality really tells us that this fundamental and applied approach are much more closely related than it was ever thought. Okay, so previously it was thought that people dealing with quantum gravity, from the other point of view of the other physicists, they were considered a bit, very fundamental, worrying about these aesthetical problems and not really interested in explaining processes in the lab. But now actually this idea of finding a theory of quantum gravity has given us a new tool to actually make some useful predictions for things that happen in the lab. And I think that's super interesting conceptually. And this is also something I hope that you would be interested in studying further, because I don't think many people have realized this yet outside people actually working in gauge gravity duality. So today I want to give you some example where we can use this applied approach to actually calculate something, and I want to show to you how this works. But before I go there, I mean, are there any questions about this general strategy? I mean, I think it's very important to understand. I mean, this is what I want you to understand, and now I'm just going to give some examples. Are there any questions?
I mean, maybe I have a question though.
Yeah, sure.
It is maybe too general, so feel free to just ignore it and maybe we'll answer it later. But I was interested, since we are discussing that this fundamental and applied approach seem to be more related than we initially thought, which lessons for the fundamental approach can we actually derive from the applied approach, if you think that there are any? Because there seems to be a direction from the fundamental to the applied approach where we are using techniques developed in gravity to study strongly coupled quantum systems. But I was curious if there is anything that you can learn about quantizing gravity from what we are doing in the applied approach, studying strongly coupled quantum systems, or to enrich our understanding of quantum gravity.
Yeah, I think that's an excellent question, and I wish I knew a full answer. Okay, so I think this is just a matter of research right now, and there's many people are interested in this, but there's no universal answer yet. Maybe to be a little more specific, okay, so if we learn more about which theories and which gravity duals are relevant in this lab context, I mean, that might give us some new ideas about, how to quantize gravity. And certainly one idea which I would like to mention is the topic that is discussed widely at the school, which is this relation between quantum information and gravity. So there's this whole area which is called bulk reconstruction. And so this started from this concept of this entanglement entropy, but this has been pushed quite a bit further now. Okay, so I think as many lecturers discuss at the school. And so where really information concepts in these strongly coupled theories are represented geometrically. And so there's this new relation between information in quantum field theory on one hand side and its geometrical realization, which then tells us about the structure of gravity. I think this is a fundamental new development that will, I hope, will bring us forward quite a bit also in making progress in having a quantum theory of gravity. I mean, certainly, I mean, there's a very big area of research right now where people study the quantum nature in black holes. I should say, but of course, these are black holes in anti-de Sitter space. Okay, so they're not really the black holes we see in our galaxy, for instance. But the hope is that by learning something, I mean, physicists always study simple problems, even if they're not totally realistic. And then the hope is that in the next step, we can draw conclusions for the systems that actually appear in the real world. So there's a very big effort of studying the quantum nature of black holes in anti-de Sitter spaces, starting from these in quantum information concepts in quantum field theory, in the dual field theory. And so I think quite a lot has been learned about, about black hole evaporation and the black hole information paradox and all these things. So there's really been progress in understanding this better at the theoretical level. But however, of course, it's for black holes in anti-de Sitter space, and we know that our world is not an anti-de Sitter space. But so just to give you an example, that the arrow doesn't just go in this direction; it also goes in that direction. And this is actually something I would hope for the future also to make significant more progress and to make further advances in this direction. Okay. So, okay, let me just say at the moment, this is a very general statement. And okay, so the examples I'm going to show today, they're mostly about learning something about strongly coupled systems using ADS, the gravity dual. But certainly it's also possible to learn something about quantized gravity using the arrow in that direction. Okay. So one point I should make is that, of course, the ADS-CFT correspondence was found proposed in 1997, which is now 25 years ago. And of course, a lot of progress has been made in the sense that at the beginning, there was this one example of these rather abstract theories with a lot of symmetry, but now there's quite a lot more dualities, which also brings up this question. I mean, can you formulate these dualities also outside string theory? And of course, many things have been conjectured, but the one which is still under the best control is the one in string theory still. But this doesn't mean that there's been a lot of, there's been a lot of other progress, also in areas neighboring string theory, I would say. Okay, I hope this was a kind of answer to your question, but if you want, I can talk maybe tomorrow a little bit more about these quantum information things and how the arrow also works in this direction and not just in that direction. Okay, but I really want to claim that, okay, more information has been going in this direction, but some has already been going in this direction, and this is something I hope will happen more in the future. And so it's really a relation rather than being an influence of one on the other. So this is really something I would like to claim here in these lectures. Okay, did this answer your question?
Yeah, no, yeah, I think that it answers my question. No, yes, I think it's fine. I mean, the only other thing that I would say is that, I mean, the examples are fine, the only thing, the only example more that I was curious if there was anything, any work in exporting some ideas developed there to gravity, or stuff like using gravity to understand things like QCD and related theories, and if that can tell us anything about gravity. But from the example that you give, I guess that is more purely on the applied side, and there is nothing going back towards the fundamental side, I think, in that area at least.
Okay, yeah, okay. I have one example about QCD right now, and maybe I will show you this example now, and then we can discuss some more if you know what the status is. I mean, the thing, of course, the problem which arises a little bit is that if in ADS-CFT, because of these many symmetries, everything is under excellent control. Now, if I want to describe QCD, of course, I have to break some of the symmetries. Okay. And then if I break symmetries, then automatically things become more complicated. Okay. and then it's harder to draw conclusions. But so, okay, let me go to my example in QCD, and then I will come back to your question at the end. And, okay, so that makes a very nice connection to the examples. Okay, so let's deal a little bit with this applied approach now. Okay, and I mean, the shear viscosity over entropy example, which I just flashed, that was, of course, the most famous example at the beginning, but there's different ones which I worked on also, and which I would like to show. Okay. So what I'm going to talk about now, I mean, is applications to strongly coupled systems. And in particular, now I want to talk about QCD first, and maybe a little about condensed matter later. Okay. And so I should say that, I mean, this is in physics, the paper, is it cited somewhere here? Yeah, okay. So if you see this paper, so this is a paper which I wrote almost 20 years ago with colleague Nick Evans in Southampton. And so this was when I was still at Humboldt University in Berlin, so quite some while ago. And I mean, if you check my citations, this is still my most famous paper. Okay, so and this is about studying properties of QCD using the gravity dual. Okay, so I mean, there's this, of course, the super famous example of the shear viscosity over entropy density, but I just want to say there's also other examples, and the one I'm going to focus on now is because I mean I worked on this quite extensively. And okay, there's also a review article about this from 2007, I think, by also with Nick Evans and Ingo Kirsch. And so if you're interested in that. So this is about QCD and mesons in ADS-CFT and gauge gravity duality. Okay, so let's go to this example. Okay, so as I told you, ADS-CFT works very well, although there's no proof, but there are some very, very good arguments why it should work, especially the symmetry and the number of degrees of freedom. So all very well and very good, but so now can we apply this to something in the real world? And then immediately there is this problem that we have to relax some of these symmetry requirements because just our world is not so symmetric, okay? And so now the question is, can we relax them in a controlled way? And at least some of them we can relax in a controlled way. So, and the first step is that we have to get rid of the conformal symmetry that we have in this conformal field theory, because QCD is just not a conformal field theory. So we have to do something about it. And then we can study the so-called renormalization group flows. Okay, I'm not sure if everybody's familiar with this, but so this is a fundamental concept in quantum field theory, where you go from very high energies to very low energies and see how the coupling constants in the quantized theory evolve under this change of scale. So the tail is a scale you have to introduce for regularization, but then it also tells you at which energy the physics happens that you are considering. Okay. Okay, and then, as you probably know, QCD is also a theory that has the property of confinement. And I mentioned this briefly yesterday. So if you have two quarks or a quark anti-quark in a meson, and then they almost, it's just the inverse of two electrons. So if you have an electron and a proton and they interact with the electromagnetic force, then the strength of the force goes with 1 over r squared. This means, if the charges are very close to each other, they interact very strongly, but then if we take them far apart, infinitely far apart, they will not notice each other anymore. Okay, so that happens if you have two electrical charges. But in QCD, it's the other way around. Okay, so particles interact very strongly if they are very far away, but they interact very weakly or they're almost quasi-free. And so this is this asymptotic freedom, which you may have heard about when they are very close to each other. Okay. So and so this confinement is a kind of hallmark of QCD. So if we want a gravity dual of QCD, we should describe confinement in the gravity dual theory. Okay, so now there's some more technical issues. So, and one of them is that we need more degrees of freedom than, so in this original conformal field theory that I mentioned yesterday, this NX24 superunion Mills theory, which is this prototype conformal field theory that enters the ADS-CFT correspondence. So in addition to the conformal symmetry, there's actually supersymmetry. And that means that the field content of that theory is extremely constrained. Okay, so you cannot add any fields to its Lagrangian, because then you will automatically break the supersymmetry that the theory is supposed to have. Okay, so it's a gauge theory, but then we have 4 fermions and 6 scalars. So remember, the 6 scalars came from the fact that they correspond to the 6 dimensions which are transversal to the D3 branes. Okay, so they have this geometrical meaning. And so this means I have 1 gauge fields, 4 fermions, and 6 scalars. So this is the field content of this theory. And if I remove or add anything, I will break the symmetry that the theory is supposed to have to enter this ADS-CFT correspondence. Now, the problem is that although we have fermions and scalars, well, in QCD, there's fermions, but there are no scalars. And, but I mean, you can kind of argue that when you go along such a renormalization group flow, that the scalars become very massive and they decouple and you don't have to worry about them anymore, which of course then breaks the symmetry. But then there's another issue that due to the fact that everything is in the same supersymmetry multiplet as the gauge field, that all the fields transform in the so-called adjoint representation of the gauge group. And this means that they cannot be used as a field describing quarks, because the quarks are in the so-called fundamental representation of the gauge group. Okay, I don't know if these things mean anything to you. I just wanted to say, so although there are fermions in this conformal field theory, they have properties which exclude them from being able to describe quarks. But if we have,
Are you still on slide 37, right?
Yeah, I didn't move anything. Can you see my mouse moving?
Yes.
Yeah, I'm still talking about the same slide. Yeah, sorry.
Just to be sure that
Yeah. Okay, so sorry. Yes, I maybe I should have written this down. Okay, so do I have this somewhere? Okay, yeah, okay, so I see you want this written down. Maybe I should just take my, okay, let me keep talking, but I will unpack my, okay, while I'm doing this, I mean, was this completely incomprehensible what I just said? I just wanted to say that the fermions that occur in this theory that we have, they cannot be used. Oh, wait, I think no, probably I cannot connect to the internet. Okay, I will have to arrange this for the next hour because I'm in another place than yesterday. Sorry. Okay, let me do this later. Okay. Let me explain like this. Okay, so yesterday I wrote for you this Lagrangian. Okay, so the Lagrangian of NX24 superunion Mills theory. And this has a gauge field and fermionic fields and scalars. And the symmetries absolutely constrain this field content. But the problem is that these fermions that are in the theory, they have properties which exclude them from describing quarks. Okay. So all I wanted to say is that now we have to add some other degrees of freedom, other fermions, which have this property of being in the so-called fundamental representation of the gauge group. Okay, and so this means that also on the gravity side of the correspondence we have to add something. And I will show you how. So now, depending on what you want to do, if you would want to describe QCD, and so the theory of the strong interaction, you want to add quarks. If you want to describe something in condensed matter physics, you want to describe electrons. Okay, and this can also be done in a similar way, but okay, for the moment, I'm sticking with the quarks because I'm just talking about quantum chromodynamics here now. Okay, sorry if this was not very clear. Okay. Okay, I just wanted to explain these 2 points. Okay, so ADS-CFT is very beautiful, but it doesn't describe the real world because it has too much symmetry and it doesn't describe the degrees of freedom that we need in quantum chromodynamics. Okay, that's all I wanted to say. And but there are some ways of getting rid of this problem. And so let me show them to you. Okay, but I should say one thing right from the start. So there was a third point yesterday, if you remember. And the third point was that this limit. Okay, so there's this limit that we have to take this n. Can you see my mouse moving here? Okay, so there was this limit that we have an SUN gauge theory, and inherently in this entire construction, this n has to be infinite, because that corresponds to the low energy limit, which takes us from a quantum gravity theory to a classical theory. Okay, so if I don't take this limit, then it means I'm in the regime of quantum gravity. And yesterday I discussed at some length that we don't really understand this quantum gravity. Okay, yesterday I explained to you that this corner here is not under a very good calculational tool. I mean, you can write down a Lagrangian and say it should be quantized, but okay, nobody knows how to do this explicitly. Okay, so this means here we cannot really explicitly work. We have to take this limit to be here. Okay, so here we just have the Einstein-Hilbert action, and it's classical, and we just solve the equations of motion. So here there's no conceptual issue here in this corner. But this limit, which takes us from the quantum to the classical theory on this side of the duality, is precisely this limit which takes us from the standard SUN theory to the limit where n is infinite. Okay. So this means we cannot get rid of this limit, otherwise we just ruin the entire construction. Okay, so we have to, if we want to do explicit calculations, we have to work in this limit at the bottom part of this diagram. Now, so the problem is that QCD is an SU3 gauge theory, so, and then which means that n is equal to 3. Okay, and 3 is certainly not infinity. Okay. So, but we just have to live with this. I mean, so I told you that in QCD is a strongly coupled theory, so we don't know how to solve it. And now the idea is, let's get some fresh ideas from the gravity dual. But then the issue is that we can only get these fresh ideas for the SUN QCD, not for the SU3 QCD. But then the idea is to say, well, okay, but we can't do any better. So let's hope that there are at least some physical questions that we can address, even though we are in the wrong limit. And this is again this issue of universality. Okay, so since we have the universality, so maybe some properties of QCD we can describe, although we know that the theory we look at is not exactly QCD, it's a large n version of QCD. Okay, so is this clear? So we cannot just use a Lagrangian and work from there. We just say, we know our gravity dual describes a different Lagrangian. However, it might be the case that some physical properties are nevertheless described by this. And then let's see what we can predict for those. And so this example I'm showing to you now is precisely in this category. Okay, so I can make some statements about QCD, although I know that the Lagrangian my gravity dual is describing is not exactly QCD. It's a theory which is similar to QCD, but it's not exactly QCD. And so the art of this entire area of research, okay, is that you can use this gravity dual to describe some strongly coupled system, and that's very wanted because there are not many methods around to describe strongly coupled systems at all. However, you know, the art is to find exactly where this is applicable and where not. Okay, maybe this is a bit abstract. Let me go back to the example and then you can see this better. All right, okay, so if we want to describe some QCD, so the question is, how close to QCD can we get? And I can tell you that we can get the symmetry requirements relaxed in a controlled way. And we can add these degrees of freedom, which are these quarks, okay? But so what we can't do is to undo this large n limit. So we just have to live with this fact. Okay, so let me give you a brief impression. So how this is done. Okay, so first of all, we have to have this RG flow and we want a theory with confinement. And so just very pictorially how this is done. So remember, this was my the black object was my cartoon of an anti-de Sitter space. So, the anti-de Sitter space is in 5 dimensions, and my boundary theory where QCD is defined is in 4 dimensions, and so is at this boundary. Okay. And now I say, well, but this configuration is too symmetric. And so it doesn't describe QCD, so I want to break the symmetry. And so then literally what we just do is we deform our beautiful anti-de Sitter space, sorry, and making something more ugly and complicated, still a solution of the equation of motion law, in such a way that we only realize the symmetries of QCD, the global symmetries of QCD, and not those of this NX24 super young Lewis theory. Okay. So, so we deliberately make our model more complicated and more ugly, but if we want to describe the real world, then this is what we have to do. And so there's a nice feature because this extra dimension, which we had before, so we know our world is in 3+1 dimensions, but from this entire ADS-CFT construction, we get an extra 5th dimension automatically in the construction. But this 5th dimension now gets a very nice interpretation, because it can be interpreted as an energy scale of this renormalization group flow. Okay, so if we go from very high to very low energies, so it means that if we are here, we are at very high energies, but if we go there, we will be at very low energies. Okay, so this extra direction here gets an interpretation of an energy scale, but so since QCD changes with the energy scale, this is actually a very wanted feature. Okay, are there any questions on this? I mean, just tell me if you have a rough understanding, because I don't want to swamp you with lots of technical details if you say this is totally incomprehensible. I mean, yeah, you know, I can explain it one more time if you want. Or so, do you have any questions? I mean,
for me, it's fine. I think I'm following. So
okay.
The idea, just let me check, would be that we have this QCD at high energies on the boundary, and then as we move towards the deep interior of the ADS space-time. Yes,
exactly.
We move farther at lower energies, and so basically the space-time in some sense is deforming as we move inside. The metric is in some sense changing to account for the fact that as we go to lower and lower energies, QCD changes. It is not a conformal theory, right?
Yes, exactly. That's what I wanted to say. Yes, thank you very much. Okay, it's good to get some feedback. Okay. Thank you. Okay, let me go on. Okay, so exactly as it was just explained, so we have now the scale dependent. And then also our original theory has a lot of supersymmetry, and also QCD is not a supersymmetric theory. Okay, so we have to get rid of that as well. And that's, you know, I told you, because we start in 10 dimensions, in addition to the ADS5 space, we have 5 more dimensions which we have to fill with something. And in the original ADS-CFT's correspondence, this was just a sphere, a 5-dimensional sphere. So round, beautiful, ideal, and so on. But if we have this round, beautiful, ideal sphere, then automatically in the field theory we will have a lot of supersymmetry. And now this we don't want anymore. So we have to make this somehow wrinkly and not so beautiful. I mean, similar to here, to get rid of the supersymmetry. Okay, but this is something that can be done. Okay. So then we get a theory which describes like the gauge fields in QCD, and so the Young-Mills theory. But then I said, okay, now in addition to having this running gauge theory, we also need quark degrees of freedom. Okay, and now these quarks, they have one property, that is the way how they transform under the gauge transformations. And in the gauge transformations, they transform in a very different way than the fields that are in this NX24 super Young-Mills. And okay, so, and this means we have to add something to our gravity theory. And so in addition to having this ADS5 times S5 space, we have to put more of these branes, okay? So, and now for some complicated reason, we have to add so-called D7 branes, okay? So here in this table, you see the time direction and our 9 space directions. And so before we had n D3 branes, and as I mentioned now many times, this n has to be infinite, okay? So, and these fill the directions, the time direction and 3 of the space direction. And now it can be shown, so this was in this paper which I wrote in 2004, and so that you can actually get those quarks degrees of freedom if you put a small number of these D7 branes, and D7 means they have 1 time and 7 space dimensions, so they fill the direction 0, and then 1, 2, 3, 4, 5, 6, 7, okay? And so if you put them there and then look at the low energy limit of further open strings but that stretch between these branes, then you can actually describe quarks and mesons in your theory, okay? And so then, in fact, we can show that the meson masses, okay, so a meson is a particle which is made out of a quark and an anti-quark. And so normally it's impossible to calculate the masses of these particles directly within QCD, except using, say, lattice gauge theory or so. So, I mean, okay, as always, there's a grain of salt, but for the sake of the argument, that just is impossible. So it's, this is very difficult. And here, so what we can do is to actually calculate the meson masses from the fluctuations of this particular D7 brane. So this means in our 10-dimensional space, this is our anti-de Sitter space in 5 dimensions, and this gets totally filled by this blue D7 brane. But then we have an S5, and this S5 is in the 5, 6, 7, 8, 9 direction. And now we have this D7 brane just wraps 3 of these, and 2 of them are empty, okay? So this blue line now corresponds to these 3 additional dimensions, and then I can just study how this fluctuates, okay? And the energy eigenvalues of these fluctuations, they will give us the masses of our particles in the dual gauge theory. So this is this blue thing, so this picture here at the bottom is now what happens on the gravity side. And from the eigenvalues of these fluctuations here, we can calculate the masses of these quark-anti-quark pairs. Okay, again, to make a long story short, we can add these degrees of freedom that we need to describe QCD. And at the same time, it provides with a nice geometrical picture of actually calculating the masses of these particles by just looking at fluctuations of this geometric objects in this higher dimensional space. Okay, so maybe this again, if the question, you know, what happens to these extra dimensions? I mean, they become just you know, very, very handy to have a geometrical realizations of the observables in the dual gauge theory. Okay, maybe I shouldn't explain too many details, but so the upshot of this paper, which I advertised, okay, was that using this approach, so where we map our QCD to as the best we can to something geometrical in the gravity theory, we can actually realize this so-called property of spontaneous chiral symmetry breaking. Maybe you have heard about spontaneous symmetry breaking. So there's the story with this Mexican hat and so on, that, you know, you have a new vacuum forming. And so this is something which is very much discussed in physics in various circumstances. And spontaneous symmetry breaking is a really ubiquitous concept in physics. Okay, so and so this means that the theory goes to a new ground state. And this means that there's a concept which is the so-called Goldstone boson, because if you look at this ball, there's a mode, you know, where the potential is absolutely flat, and this is if you move along this Mexican hat, the bottom of the Mexican hat. So this is a reduced symmetry that you still have. Okay, and the bottom line of this paper is that we can realize precisely this concept, which is an inherently field theory concept, and realize in QCD, we can realize this in this gravity picture. And then if we look at the fluctuations, as I just described, we can calculate the masses of the particles by a gravity calculation. Okay, so we have a dual gravity calculation of the particle masses. Okay, and so the very nice thing is that we can compare our results to something which, to results that were obtained in lattice gauge theory. Okay, so let me explain the philosophical significance of this picture. Okay, lattice gauge theory is a computer-driven way of solving QCD at low energies. Okay, and so people invest a lot. I mean, this got very, very powerful now with new computers and so on. And so in lattice gauge theory, space-time is discretized, and then people can calculate, for instance, these meson masses as well. Okay. And so here in this picture, there is a comparison between this method. So lattice gauge theorists are people working in QCD, and so this is a very well-established method, and you know, very successful and so on. Now we, the ISSPP people, the gauge gravity people, arrive and say, okay, this is an example where we can test our method, because we can now, with this gravity calculation, which I showed to you, also calculate these meson masses. Okay. And the surprising result of that is shown in this figure, that our result agrees extremely well with their result. Okay, so it's, for philosophers, the interest is really that, you know, we talk now to these lattice gauge theory people who normally say, oh, these string theorists, you know, they are always in the clouds, and, you know, we don't know what they're doing. Is this useful? And now we can do a calculation that we can directly compare to what they are doing. Okay. Yeah.
Question. Can you say something more about this result? It seems very, very interesting. I would like to know something more about why the gray zone is so. Is it a mistake? What is that?
Yeah. Okay. Yes. Okay. I'm going to explain in detail what you see in this plot. Okay. Okay. So I will definitely do this right now. So I just wanted to advertise why this is interesting on general grounds, is because it's really a combination of an ISSPP calculation or gauge gravity duality calculation using the methods I described on the previous slides with something that the lattice gauge theorists do. So actually this picture is also in my book in chapter 13 or something like this. So if you want to look at all the details, it is actually in the book. Okay, and actually some lattice gauge theorists drew this picture for us, which was very kind. Okay, let me try to explain what exactly we compare. And so these colored dots are the results of the lattice gauge theorists, and the result of the ISSPP or gauge gravity duality computation is this black line. Okay. And so in principle, now we do, both communities do the same calculation, but I should say that the lattice gauge theorists, they needed 6 months on a supercomputer. But if you believe what I told you in the last 15 minutes, then my PhD student can do this calculation on his or her laptop in 1 afternoon. Okay, so we are, at least, if one thing, we are much faster. Okay, and so let me explain what is compared. Okay, so as I said, in ADS-CFT, we are forced to have n infinite, and not n is equal to 3. And in lattice gauge theory, of course, calculations are simple if n is small, but they become more and more hard the larger n gets. And certainly they can't get to n is equal to infinity. So what was done by the lattice gauge theorists is that they did the calculation for different values of n, so increasing values of n. I mean, for them, 17 is already almost infinity, because the calculation becomes very involved. And so as you can, so what is plotted here is the mass of the rho meson. So this is one of these mesons in QCD as a function of the pi meson mass squared. Okay, so the pi meson is actually one of these Goldstone bosons, or it then becomes a pseudo Goldstone boson. So one of these particles that is light in QCD due to this spontaneous symmetry back here. So, and of course, this is a particle with a definite mass that you measure in the lab, but here, just for the sake of the argument, we allow this mass to vary as a parameter. Okay, so now the goal is that we want to compare the ADS-CFT calculation with the lattice gauge theory computation. And so the first thing, if you compare two completely different theories, you have to match the scale. I mean, there's one parameter which you have to match. Otherwise, you can't compare anything. And the parameter that is matched is the value of this rho meson particle at vanishing pi meson mass. And this is called m rho 0. Okay, so this means at 0 pi mass. So when this is 0, I choose my m rho to be exactly m rho 0. And that's why everything starts at 1 here. Okay, because at 0, m rho is m rho 0, so then this ratio is 1. Okay, so this is where we match the scales, so the lattice gauge theorist and us. And then we choose this m pi to be a parameter in our theory, and so our result is that we almost get a straight line. I mean, it's literally straight. I mean, maybe at the very end it starts deviating a little bit, but essentially the ADS-CFT computation gives you the straight line. And so the lattice gauge theorists, of course, because they do many computations, they can do an honest, how do you say this in English, error. They can estimate the error. In our case, there's not much error we can estimate because we have only this one model and we solve one classical equation of motion. Okay, the good thing is we just have to do a classical computation. And we just solve this classical equation of motion, so we cannot really have an error because, I mean, the solution is just the solution. So this means we just get this line without a possibility of giving any error. But the lattice gauge theorists, they can extrapolate. So using this increase of n, they can really extrapolate to infinity. And what they say is that their results will, for any value of n going up to infinity, will be placed in this gray region. Okay. Okay, and so now the upshot is that our line that we get with this gravity, so we solve a classical equation of motion in the dual gravity. They solve QCD on a supercomputer, and we get results that coincide, because our line is always inside their error bar region, okay? And that's fantastic, okay, because, two completely different calculations, and we have this assumption that ADS-CFT is true and so on, and also works for this deformed, modified setup, okay? apparently this assumption is meaningful because our result coincides with their result. So that's wonderful. But now we can come back to this question that somebody asked earlier, can we go the other way around? I mean, do we learn anything about quantizing gravity from this applied result?
Is there something I didn't understand well?
Yeah.
Is there something that is measurable here in the lab? Is a ratio between the masses of the mesons is measurable?
Yeah, this is okay. Yes, okay, very good question. Yes, so for academical purposes, okay, in this calculation we allowed this mass to vary, okay, but so in the lab this particle has a value which is, I think, something like 100 mega electron volts. So this is a known particle, and then also this. I mean, here we just normalize to some scale for the sake of the argument, but you could also plot the same plot in using mega electron volts along this line. And then this would mean that we sit at some particular point on this line. Okay, so one point on this line corresponds to the physically observed value of this pi meson. Okay, and then we see that there's agreement with this error bar. Okay, so I would say for the sake of the argument, we allowed this to vary, but one of the parameter values of this m pi on this line corresponds to the physically observed value. Okay, and then so we have consistency with the experiment here. So on one hand side, this is nice, but of course, there's a slight caveat because, of course, what we are looking here, we can only look at ratios between particles. Okay, we cannot make absolute predictions for the mass of a particle. We can only say what is the ratio of the mass of one particle compared to the mass of another particle. And that's because there's always this issue of fixing a scale. Okay, so we have one parameter. I mean, our model has very few parameters. Essentially, it has only one. Okay, and this one parameter is the scale. And so once we fix the scale, then we can make predictions. And if we fix the scale at such a way that we just hit the physical value of this pi meson, then we predict the rho meson, and it agrees with the the red circles are the one for QCD, so the ones observed in nature, and so it works. So I hope that answered your question. So yes, we can compare with experiment, and yes, it works. But here, just to compare the two theories, we looked at more values of the pi meson mass than the one that is observed in the lab. Okay, so I was saying something else before. Okay, yeah, so I mean, now there are many questions that are attached to this plot as a fundamental question. Okay, so it works extremely well, but so what is quite unclear is why does it work extremely well? Okay, so and this is very hard to answer this question because you know. Okay, all of these long things that I explained here with all these slides. So we modified ADS-CFT. So we ruined the symmetry. So we break it quite heavily, and we add this extra blue D7 brains. Okay, so we really changed quite a lot the original ADS-CFT correspondence. And okay, so then of course by doing so we lose a lot of the control. I mean, there's not as much control as in the original example of ADS-CFT. And so for that reason, it's now quite hard to say what do we learn about quantum gravity from our model. You know, we have a very complicated model, and so it's amazing. It's really reassuring, wonderful that we get so good agreement with experiment and with this lattice gauge theory. But on the other hand, now the question then, of course, is immediately, okay, if this works so well, it must tell us something about our quantum gravity theory. But that's much harder to answer what exactly it tells us. I mean, we of course, you know, people think about these things, but it's not so easy to make progress there. And but I should say then, of course, universality is again an argument that comes up right away, because you can see, so in the lattice gauge series, they did the calculations for quite a lot of values of this n, so which each of them corresponds to a different Lagrangian, if you want. And you can see that, I mean, here especially, I mean, there's not a lot of variation between these, okay? So there, I mean, regardless of what this value of n is, here, for instance, if you look at this dot, they're almost all on top of each other. Okay, so and this is another example of universality. So it seems to be the case that the results doesn't depend on this n. Okay. So if the result doesn't depend on the n, then okay, then any theory for any n can describe the physics. and so, you know, and to some extent, the result doesn't depend on the microscopic structure of the degrees of freedom. And that's called universality. And I mean, that happens not very often, but significantly often in physics, that you have this universality. And so as ADS-CFT predictions seem to be good precisely if you hit such an universality example, because then, you know, the microscopic, this precise nature of the microscopic degrees of freedom doesn't matter, but what really matters is the fact that they are strongly coupled. And that's where ADS-CFT is good. So we can, in some sense, in selected examples, make predictions, even if we don't exactly describe the Lagrangian that we should have. So that's one of the points also I want to make. Okay, I think it's good time for a 5-minute break, unless if somebody else wants to ask a question about this picture and the lessons drawn from this. I don't know what do I have on my next. Okay, yeah, okay, so here just, you know, so what really, we have to match this coefficient here in this ratio, but then what we can compare is the slope of this line, and so that's our result. And the lattice gauge theorists, they are all Italians actually. They work in Great Britain, in Wales. So that's what they got. Okay, so you see we are within the error basket. Okay, are there any questions about this?
I mean, maybe just something very quick. Yeah. So, I'm not entirely sure that I understood the geometric picture behind the computation, right? Yeah. Because my impression was that we wanted to. Oh, okay. So it is exactly this one.
Yeah, exactly. That's why I explained. Okay, I think. Sorry, my pedagogical strategy was not very good. I gave you.
I mean, I probably missed that. I just missed that part. That's my bad. Okay. Then it's fine.
Okay. So this plot, which I explained to you, is precisely obtained with this method that was explained. So we deform, we put this blue structure, we look at the fluctuation, and this is exactly. I mean, I was really exactly describing how we get this black line here. Okay, so that's why I explained all these details. You know, I just wanted to say there's a complicated way of deforming the original correspondence to get the features that you want in QCD. And those allow us to calculate this black line, and then we compare what the lattice gauge theorists do.
Okay, I see.
Yeah, thanks for asking again. Yeah, sorry. I think I started immediately with the details. I should have told you where I'm going first, and then I wanted to explain to you how to obtain this line, and so this black line is obtained in a gravity calculation where we significantly modified the original ADS-CFT correspondence in such a way as to get more features that QCD has, as many as we can. And then we look at these geometric fluctuations and solve classical gravity equations of motion, and then we compare to the lattice gauge theorists, who of course work in the quantum field theory.
So basically, the basic geometric picture is the one that you described before, but then the details of the deformation is what goes beyond, let's say, what we can discuss now, in a way.
Okay.
Right.
Okay, so I should say, if you're really interested in the details, so first of all, I think, you know, if with all the information I've given you, I mean, it shouldn't be completely impossible to read this paper, okay, at least the introduction, but also, you know, okay, so this is my most famous contribution to the subject. So if there is quite a bit of discussion in my book about this, and also this plot is also explained in the book. So I hope that given the information I've given you, yeah. So one thing is, there's this, so let me just recapitulate briefly. So the deformation of the space breaks the symmetry to what we have in QCD, and the adding of this extra branes gives us the quark degrees of freedom. So because a meson is a quark anti-quark, okay, and so with these two ingredients, we arrive at a new gravity theory with different equations of motion that we solve, and the energy eigenvalues we then compare with the meson masses in QCD. So here I've just shown a very general deformation that we use one in particular that reduces to the global symmetries that we have in QCD. Yeah, so that's the idea. Okay, so if you're really interested in more details, if we take a 5-minute break, I can look in my book in which page actually you find this, and I can tell you. So I think, if you're interested, it's not impossible to understand now more details based on what I explained to you. Okay, so I pushed something probably. So the best known example is this, or I should say, involves nx24 SUN super young Mills theory. So this is a theory which is a gauge theory. So the Lagrangian starts with this, okay, and then there's 4 fermions and 6 scalars. So the 6 scalars we identified yesterday as being associated to these extra dimensions. So this is a conformal field theory, which means that it's scale invariant. Okay, and so there's no running of the couplings. And so the other thing is that due to the supersymmetry, all fields that's a technical term, I'm going to explain it in the adjoint representation. Of the gauge group. And so this means, what does it mean? So if I look at how this field strength tensor transforms under gauge transformations, it transforms like this, okay? So if the gauge transformation of this SUN is given by this function lambda, then that's what I have. And now the supersymmetry means that the fermions and the scalars, they have to transform in exactly the same way. Okay, so all of the fields have to transform in this way. And now I have to contrast this with QCD. So, and QCD is a different gauge theory where, okay, so, okay, it also starts with the field strength tensor, but then I have some fermions which are the quarks. Okay, so the Lagrangian is written in such a way. Okay, so this is essentially a covariant derivative for fermions. Okay, so then you see we don't have these scalars, but then the main difference is that, so first of all, the gauge group is SU3. So this N which we had before is now 3. And so, but then the other point is that these psi's, sorry, this thing just transforms like this under the gauge transformation. Okay, so if you compare with this fermion here in this the adjoint, you see there's a factor here and there's a factor there. But if we want a quark, there's only one factor here and there's nothing here. Okay, so this field doesn't appear in my original Lagrangian. In this Lagrangian, there's no quark. Okay. So if I want QCD, sorry, yeah, so there's no quark there. But if I want QCD, I need quarks, okay? And so this whole gymnastics, which I did, okay, so to, and then on my slides, I told you on the gravity side, so we have this space, which is ADS5, and then it's a product space with this S5, and then I put this blue brains. Okay, so I put a brain here, and then it was roughing here, and then there were the fluctuations here. And so this whole gymnastics is done for the reason that, now I can go back to the table that I drew yesterday. 1 second. Yeah, okay, so this table I drew yesterday. And so we had these 3 brains. So these are the dimensions. And now to get the quark degrees of freedom, I put D7 brains on top of this. So, and because they're D7 brains, they span in 7 + 1 dimensions. Okay, and then so yesterday, I explained to you that our gauge field, so which enters this F mu nu, corresponds to an open string which begins and ends on this D3 brain. And now if I have this big D7 brain, it will also extend in those directions. And then I can have different strings that begin on this black D3 brain and end on the blue D7 brain. Okay, from the D3, they go from the D3 to D7. And this means that these strings, they have only one endpoint here, whereas these strings, they have 2 endpoints here on this brain. Okay. And these endpoints, they are associated with these gauge transformation properties. So now this means this A mu or this F mu nu field, from this construction, I already see that my F mu nu transforms like this. But the quark that is associated to this, because it has only one endpoint here, this will transform just like that with nothing on the other side. Okay, and this is precisely what I need to have a quark. Good. Any questions about this?
I have a problem with the scale of energy, because brain are much lower, much higher energy than quark, or I am saying something mistaken.
No. Okay, yeah, very good question. Okay, so then let me go to what I was talking about. Let's see if I have a nice plot here. Okay, so here there's this very busy. Okay, this is what I drew yesterday. I realize it's a bit busy, but I hope you, especially if I now start drawing things in the middle of this, on top of this. Okay, let me yet choose another color, maybe. Okay. So now every day from yesterday is in blue, black, and red, and everything I'm explaining now will be in green. Okay, sorry for the. So yesterday I was explaining this low energy. So this is meant to be energy limit. Okay, and okay. So let's go back to what we were doing yesterday. okay, yesterday we were looking at this, and so I was discussing the branes and the strings at the very high energies, okay? So, and now these D7 branes, they added, sorry, they are added at this level of the discussion, but these extra branes, they also have a particular behavior in this low energy limit, okay? So if I can show that putting these D7 branes here and then taking the same limit as I was discussing yesterday will precisely give me these extra fields in this theory here. So, or to go to this slide. So this is at the level, the branes and the strings, they are at this level here, okay? But so what I was explaining about adding these branes as at this level here, but this limit that I'm taking is also well defined for these D7 branes. And if I put these extra branes on top, then here I get my SUN gauge theory plus these quark degrees of freedom. And here I get classical gravity plus an action describing the fluctuations of this embedded surface. Okay, so in this corner, I now have this picture. Okay, so this means in addition to having the Einstein-Hilbert action for which the ADS space is a solution, I have another contribution to my action, which is the so-called Dirac-Born-Infeld action that describes how this brane fluctuates. Okay, so the statement is that I can redo the same limits as I did yesterday with this additional features. And then again, I get the quarks in my quantum feasible Lagrangian in this low energy limits where the branes are no longer visible. I hope that explained the question.
Sorry. So perhaps one could say that confinement is a gravitational effect, or it is too much.
So say once more, I didn't hear acoustically. What is a gravitational effect?
Sorry?
Can you just repeat the question? I didn't hear.
Yeah, if I understood well, the reason because at low energy you can have this effect based on the D7.
Yes,
rate,
exactly.
yes, through the duality. In a certain sense, one could say that the confinement of quark is a gravitational effect.
Ah, yeah. Okay. Well, that's.
It is too much. It is too.
Okay. Okay. So I would say this is a controversial thing. Okay. But this brings us to the heart of the whole thing. Okay. So the confinement. Okay. Good. Let me show. Which figure should I show for this? Wait. Let's be careful, or or modest, or so okay. So it's true that now here this theory becomes this large N version of QCD with confinement. Okay, and here now we have this slightly more involved gravity theory, which is still a classical gravity theory, and we have this duality. And again, according to this principle that I was discussing beforehand, so we have two different Lagrangians that describe the same physics. Okay. Now, what does it really mean that these effects become? I mean, okay, yeah, this is a very hard to answer question. Because, okay, so confinement happens here. So here I have these gauge degrees of freedom, okay? And so I cannot separate the quarks. And now I'm claiming, so via the conjecture duality, that the same physics is described via this classical gravity action. Okay. The slight complication now comes from the fact that because I took all these limits, I don't have such a direct control over my degrees of freedom. And I mean, what I managed to achieve in this theory was to calculate the mass of the meson. Okay, so I can calculate the mass of this quark anti-quark pair, which is subject to confinement. But since I took this limit, I cannot resolve the structure of this meson anymore. I cannot look into the meson. Okay, I can just calculate its mass as an entity, but I cannot really say what is the physics happening inside that meson which creates this confinement. Okay, so the statement is I have an effective theory by which I can calculate physical observables that can be measured in the lab. But I will be very careful about actually saying that I can explain the dynamics happening inside this meson. Okay, so there maybe I should be cautious. I mean, I think really saying that now confinement is a gravitational effect is pushing it too far. Okay, I mean this. Okay, maybe it's true. Okay, but this, I think, to draw this conclusion from what I said so far is a bit dangerous. Okay. Maybe so the thing that we can say is that we can calculate observables such as the mass of a composite object, this meson, yeah, a quark anti-quark pair which is subject to confinement. I can calculate this mass, and the result seems to be correct because I can match it to lattice gauge theory and to experiment. But I don't have enough resolution to actually describe the dynamics happening inside the meson. Okay, so this means I have an effective way of obtaining this macroscopic result for the mass of the particle, which must be due to the microscopic confinement. But since I took this low energy limit, I don't have enough resolution to really explain the cause of the confinement at the microscopic level. Okay, so this is again this universality property. I can make statements about macroscopic quantities that somehow are based on the microscopic dynamics without actually knowing the precise microscopic dynamics. So yeah, okay, so I have an effective new approach of doing calculations, but I don't have a new explanation of the microscopic dynamics themselves. Okay, was that helpful?
Thank you very much.
Okay, good. Yeah, it's a very good question. I mean, but that brings us back to this question if, also, I mean, that somebody asked before. I mean, can we now learn something about quantum gravity from these calculations that I showed you? I mean, given that my model maps so well to these lattice gauge theories, do I learn anything about quantum gravity? And the hope is there, of course, and that's what many people study. But okay, it's still not entirely clear which road to go to make these quantum gravity statements, because then that requires to undo this limit. And that's where all this discussion of these more quantum information theoretical concepts can maybe come to help. And certainly this is something that many people are working on, but I wouldn't say that we have a concrete result there yet. I mean, okay, maybe it's slightly different context than the one I was talking about here. Okay. And okay, maybe what I should do briefly is to go back to this other very famous example of the shear viscosity, this example, yeah. And so this was really the breakthrough in the sense that this is for the first time that people calculated a quantity using ADS-CFT that was successfully measured. And so it was successfully measured here at this RIG accelerator. And so this is a heavy ion collision where there's a lot of hadrons and mesons coming out of this. And so let me very briefly explain how how this was done. Okay, so then I need to share again. Because I mean that's really the key result, which is very famous and which everybody knows. Okay, so so this so the so this is this very famous paper from 2004 also. And so as I said, this eta, so assuming that you have some channel and there's some fluid moving in this channel, and then so you have one plate here, and this you move with some velocity, okay. And then now this fluid is viscous, okay. And this means that if the velocity is fast here, it will, so if the velocity is big here, it will get smaller as you move inside, because there's this friction. Okay, so there's friction. And okay, so this viscosity eta measures the gradient of okay. So and so how this viscosity, so the viscosity is a transport coefficient. Okay, so and so there's a standard way so this is in transport theory, so it's much more general than ADS-CFT. These coefficients are calculated from so-called Kubo formulae. So, okay, so this is some very standard techniques in many body physics called linear response. Okay, so this is much more general than ADS-CFT or anything. And so in this case, this shear viscosity actually is obtained from a Kubo formula, which relates it to the correlation function of the energy momentum tensor. So this is the correlation of the energy momentum tensor. Okay, so and so we have to calculate. So now ADS-CFT or gauge gravity duality provides a way of calculating this correlation function. This relation here is totally general in transport theory, but now with gauge gravity duality, we can calculate this for a strongly coupled theory. So gauge gravity duality provides a way to calculate this correlation function using gravity. Okay, so then I can, let me draw my standard picture again of my anti-de Sitter space. Okay. So this is the extra dimension, this holographic dimension. And here at the, so this is ADS or some deformed version of it. And here I have a Minkowski boundary where the quantum field theory is defined. Okay, so now we have to calculate this correlation functions where I have 2 points in space, and at each of them there is an energy momentum tensor. And now, so this energy momentum tensor has a source, so-called, and this source is a metric. Okay, sorry, X, Y. So the metric is a source. So this is a technical term in quantum field theory. Okay, so which comes for the energy momentum tensor. And this means that I get, so the correlation function is obtained from the propagation of the metric in the 5-dimensional space. Okay, so normally, the calculation that I really want to do is to do a quantum calculation here with some Feynman diagram of this correlation function between these 2 points. But this is hard to do because of the strong coupling. But then, as these people found, the propagation of the graviton in this extra dimension should, according to ADS-CFT, gives us precisely the result for this correlation function. And from this, we can read off what this shear viscosity is. And here it's really interesting because there's no other way to calculate this transport coefficient than by using, in the strongly coupled theory, than by using the gauge gravity duality. Okay, and and that's the famous result of these people. And again, they have, this is the shear viscosity that I just discussed, divided by the entropy density. And again, we need to look at the ratio to get rid of, and so entropy density, this is obtained from the Bekenstein-Hawking formula. So the entropy density is the entropy divided by the volume. Okay, but here this is given by the area of a black hole divided by I think 4, and then the Newton constant. Okay, and so this we can calculate for the gravity theory. And then so this little s enters the denominator here. And this eta is the shear viscosity that we calculate from the propagation in this extra dimension here. And then we get this universal result, so h bar over k Boltzmann. And so this number is roughly 0.08. So this is a very small number. Now, in this quark-gluon plasma, at the RIG accelerator in Brookhaven, this is measured for the QCD plasma. So this means QCD at finite temperature. And the result of the measurement is that this eta over S is, I think, about 0.1, okay? And so this should be compared with that. And so it's really getting, it's extremely close. And so this was the first example where people using ADS-CFT made a prediction for a number that was successfully measured in the lab. And here in this transport case, in the example I showed you before, I mean, the same calculation that we did can in principle also be done by lattice gauge theory, as I discussed. But here, this calculation was first done using ADS-CFT, so it was a true prediction of ADS-CFT. Okay. So, and that of course started this whole area of using this for applications. So are there any questions about this?
A couple of curiosity about the calculation of the ratio between shear viscosity and entropy.
Yes.
Yes. In the case of which fluids has been calculated, and how we are sure that the result is at least partially correct.
Yeah. Okay. So the point is that this, so ADS-CFT or gauge gravity. Sorry. Oh, what did I do? So this is a universal result at infinite coupling. So again, so there's this word universal. Okay, this is super important. And so it's at infinite coupling. Okay, so if you do this ADS-CFT calculation, this result, this factor depends on very little detail of the gravity action that you're looking at. Okay, so here it was calculated for Einstein-Hilbert, but if you modify this, not very much happens. Okay, so and then the result only depends on this number and on two natural constants, h bar over k Boltzmann. So it doesn't depend on any detail of the theory. And so the measurements that have been performed are for the quark-gluon cluster. So that's what I just mentioned. Then it has been measured for cold atoms. And now more recently also in condensed matter. So maybe tomorrow I can explain a bit about this condensed matter calculation. But so the key point is that, again, all these materials must be strongly coupled, okay? And so it's amazing that this universal result, which depends very little on the parameters of the theory, has been measured in very different circumstances at very different energies. Okay, so that's part of the excitement about this result, okay? It applies in nuclear physics and in atomic physics and in condensed matter physics. And all of these measurements compare with the same ADS-CFT calculation. So in ADS-CFT, we have very little freedom to change our gravity action, or a little bit. I mean, you can add these branes, and as I explained before, but for each of these gravity models, this result will be the same. Okay, so there's very little you can change. And that's why it's even more impressive that for all these different circumstances, the experimental result coincides with the prediction, which is due to the strong coupling, and then again to this universality. Okay, so this is again a physics result which depends very little on the microscopic dynamics of the theory. And that's always when gauge gravity duality works well. Okay, I hope that answered the question. So maybe let me. Okay, so I hope that answered your question. I should show, I looked at my book during the break, and I just want to show you where in the book you can find about these things if you want to know more details. So, okay, so there's this chapter 12, which is called Linear Response in Hydrodynamics. So and that's where we explain about this eta over S, and this calculation is given there. If you want to learn more details about this, the calculation of the eta over S is given on page, it starts on page 384, okay? So, it says ADS-CFT calculation of the shear viscosity. So there you can read the details. And then I also wanted to show you that this figure, which I showed you in the plot. So this about the lattice gauge theory that I was talking about before. So that's on page 418 of the book. So if you want to know more details, I also recommend these two chapters. So there you can read, well, we tried to give some explanations also in text about these calculations. Okay, are there further questions now from your side?
Maybe again, just a very quick question. So when you were explaining the computation of the shear viscosity over entropy ratio, so you said that to compute the entropy, you use the Becker-Stein-Hawking formula, right?
Yeah, that's right.
So should I take that as meaning that in the gravity dual, there is some kind of black hole?
Yes, okay, excellent question. Yes, okay. You found precisely what I didn't explain.
Okay.
So, yes, okay, I will explain this tomorrow. Okay, so yes, I dropped this under the table to simplify things, and then you immediately noticed. So all these calculations for the linear response and so on, they require a finite temperature, okay? And so another ingredient in the ADS-CFT correspondence, and this is something I will explain tomorrow, okay, is that one modification that you can do of your original ADS-CFT correspondence is to put a black hole into this ADS space, okay? And if you put a black hole inside this ADS space, then it means that you get a finite temperature in the dual field theory, okay? And actually, this is something very nice, and I think I will explain this tomorrow in more detail, because I mean, this is also for these condensed matter applications that I'm going to mention tomorrow. This is relevant. So a finite temperature field theory always means that you compactify time on a circle, okay? But precisely the same compactification also happens if you put a black hole into any space. Then also the time becomes a temperature. So the Hawking temperature of this black hole very naturally defines a temperature in the field theory, okay? So you can really imagine that, if you look at these finite temperature processes, that really we put a black hole into this anti-de Sitter space. And that very naturally provides us with a gravity dual of a finite temperature field theory. And of course, as is required for this quark-gluon plasma, we have to work at finite temperature. So this is one of the very nice features of ADS-CFT, that by putting a black hole into your ADS space, you very naturally define in a geometric way a temperature for the field theory, and that has lots of applications. Yeah, I will come to those tomorrow. So excellent question. Yes, I should have mentioned it, but I thought, okay, if I now mention the black hole, it will be too complicated. But precisely this calculation that I showed to you is done for a black hole embedded in the ADS space. Yeah.